I'm Kaushik Rajan from Microsoft Research India, and today I'm going to be telling you about new techniques we are building for eliminating redundant I/O from big data queries. This joint work with several collaborators at Microsoft. Let's get started. A popular way of processing large amounts of data today is to write SQL queries to analyze them and to run such queries on a cluster with many machines, or sometimes on the cloud with multiple VMs. There are several frameworks which allow for such execution, systems based on Spark, those based on Hadoop, proprietary systems from companies like Snowflake, and cloud providers like Amazon, Google, and Microsoft. All these big data systems rely on a query compilation technique that is based on database query optimizers. These query compilers take a SQL query and produce a DAG of map and reduce stages. Once you have such an execution plan, you can then run it on a distributed system by exploiting data parallelism. As I've shown on the right, each stage runs with many tasks, each task processing a partition of the input to that stage. At the end of the stage, data is repartitioned so that the next stage is data can run in a data parallel manner. This repartitioning happens through an exchange or a shuffle operator. In the big data setting, such exchanges are the most expensive operators as they require that the data be persisted at the end of the source stage to the disk and then transferred over the network in an all-to-all manner. Clearly, in a big data setting, where each exchange introduces a new stage, plans with fewer stages are preferable. Despite this, we find that state-of-the-art query optimizers produce plans with several redundant stages. We analyzed a standard big data benchmark called TPCDS, and we find that among the 104 queries in TPCDS, the Spark query optimizer produces plans with unnecessary stages in 40 of them. What the graph is showing is for these queries, how much time is spent in stages which process some data which is also being processed by another stage in the same query. So what we find is a significant fraction of queries, 25 out of 104, in fact, spend on average 50% of their time in such redundant stages. In fact, 16 of these queries spend more than half the time on stages which are redundant. We come to the conclusion that this unnecessary stage introduction is happening because today the query compiler is not built with the right set of primitives to produce a plan with as few stages as possible. This is because today's query optimizers basically do logical rewrites purely in the SQL space and are agnostic to the number of stages introduced. Introduction of stages only happens when you introduce exchanges during physical planning. What we propose instead is to change the optimizer so that you can do MapReduce reasoning right from the beginning. The goal of RESIN is to produce plans with as few stages as possible. To do this, we introduce new operators, a generic map operator and a generic reduce operator, all the way in the logical stage. And then we introduce new rules which try to pack in as many operators as possible into these generic map and reduce operators that we have introduced. And we'll go through in detail how the entire system works, but I wanted to quickly show that with such reasoning, we are in fact able to eliminate significant amount of I/O. As can be seen in the graph on the left, as we go from left to right, we are looking at queries which have more and more redundant stages. And what you will find is that as you move from left to right, RESIN is able to save more and more on I/O. And across these 25 medium and high impact queries, we are able to save about 20% of I/O. And this translates into a significant savings in CPU time as well. In fact, you will find that the cumulative savings in CPU is in fact higher. It's 25%. And this is mainly because by eliminating this redundant IO, not only do we reduce the IO, but we also reduce the IO-induced compute, things like serialization, compression, and so on. In the rest of the talk, I'm going to give you more details on what are these two operators that we introduce, how do we use these operators to produce plans with as few stages as possible, and then I'll briefly touch on how we implement this inside Spark and show some experimental results. So a RESIN map, as I mentioned before, is a generic map operator. A generic map operator is something that can take each input row and produce multiple output rows by applying some custom function. So here's an example of a query that can be implemented by a single RESIN map, which today is not implemented that way by a standard query optimizer. The details of the query are not important, but what this query is doing is it's processing the same input table IoT logs 2 times, each time applying a different filter and selecting a different set of columns, and then unioning these selected rows using a union all operator. What I show here is a standard query plan, which, as you can see here, consists of duplicate scanning of this IoT logs table, and then running computation, which is pretty much like what the query represents. There is a filter project, one for the left, one for the right of the union, and then you apply a union operator. What we do with RESIN is to produce a plan which consists of a single scan of the input table, and then we introduce a map operator, which can for each row produce more than one output, and in that way simulate the union all. So what you see here is a RESIN map with 2 contexts, which represent the 2 rows that could be output for each input row of IoT logs by the union operator. And then we add an implementation of the RESIN map, which takes the parameters that the RESIN map has and produces the code as shown here, which does what you would expect. It takes each row from the table and then applies appropriate filters and produces 2 outputs if both the filters are satisfied. As we show in the paper, a RESIN map is a fairly powerful operator. It can implement any single table query consisting of just select, project, and union operators, and it can implement such a query with just 1 stage. Next, we introduce our RESIN reduce operator. RESIN reduce, as I mentioned, is a generic reduce operator, which means that it's a key-based operator which can process all rows that share the same key and produces 1 reduced output row per key. Here is an example of a query that RESIN reduce can implement. This one again is processing the same IoT logs table 2 times. This time it's doing different filters on different columns and performing different aggregations again on different columns, though it's doing the grouping on the same column on both the left and the right. Finally, the result of these 2 group bys are combined together through a join. The query plan for this query generated by a standard query optimizer also consists of the same stages as I've shown here. What we're able to do with RESIN is to produce a plan with just 2 stages, a single mapper and a single reducer. The reducer basically is going to group on the grouping key that is shared in both these sites, which is the ID column, and then it's going to apply different aggregates on different subsets of rows as captured by the contexts here. And finally, once you do the RESIN reduce operator, you have enough information to simulate the join and replace it with just a filter. Details of how this can be done can be seen from the paper. I'm not going to also show you the resin reduce operator code. This also you will find in the paper. But the key thing to note is that it's able to compute a plan which would usually consist of multiple shuffles, and it's able to convert it into a single map followed by a reduce. Next, I'm going to tell you how we are going to use these resin map and resin reduce operators to eliminate scans and shuffles from multi-table queries. So I'll go through this query in more detail as we go through the slides. At a high level, consider a query like this, which consists of 9 stages. What resin is going to be able to do is to fuse these stages together into fewer ones as shown below. So first it's going to fuse S1 and S2, which as you can see are crossing the same input table signals into a single stage S10. Similarly, it's going to fuse S3 and S4 into S11. Once it does that, it figures out that it can actually fuse S5 and S6 together. And finally, it can fuse S8, S9, and S7, S8, and S9 into a single stage. So at the end of resin optimizations, we have a plan which just consists of 4 stages as opposed to the 9 stages that the default plan contains. So we'll go through how this fusion happens in more detail in the next set of slides. So first, observe that let's look at the operators that are happening in stage 1 and stage 2. Observe that both are, as I mentioned before, crossing the same table signals. So what resin does is to introduce a resin map operator, which does all the computation required for both stage 1 and stage 2. So the output of the fused resin map is going to contain all rows that are necessary for either stage 1 and stage 2. As a byproduct of fusion, you get also these 2 additional mappers, which are required to separate out the output of the left part of the fusion from the right part of the fusion. So in this case, these would be the filters phi1 and phi2. Similarly, we are going to fuse S3 and S4. And as these residual mappers are going to be running in the same stage as the fused part from S10, we are going to produce a disjunct of the residual filters from this fusion. So next, we are going to substitute these stages back into this query plan and then continue upwards, fusing more and more stages. So once we do this, now the next set of operators that we desire to fuse are these joins running in stage 5 and stage 6. Note that both these joins are on exactly the same set of columns, so it should be possible to fuse them together into a single stage which does the join first and then applies these filters later. Details of why exactly this transformation is this way can be found in the paper, but note that by adding a filter here, we make sure that even if the join produces more rows than required by either stage 5 or stage 6, the filter right after will make sure that only rows that are required either by S5 or S6 are actually shuffled further. Now we are going to substitute the fused joins back, and finally we are going to fuse S7, S8, and S9. And as you can notice, this is basically the resin reduce pattern where you have a single table on which you're doing 2 different aggregations on 2 different paths and joining their result together. And this can be fused together with a resin reduce operator. So this way we are able to take this query, which in the baseline consisted of 9 stages, and produce a plan with just 4 stages. In the paper, you'll find more details on these operators and the rules. In particular, you'll find what parameters the RESIN map and RESIN reduce take, what are the semantics of these operators, and what is the implementation we have for them. You'll find more details on how we are able to fuse all Spark SQL operators and clearly state the conditions under which such fusion is possible. Finally, we show that fusion itself can be done in a manner that the number of rows after fusion shuffled after fusion is guaranteed to be no more than the number of rows before fusion. And in fact, on average, you will find that number of rows shuffled will be much less, which is why we see benefits. But this requirement is critical to make sure that fusion always brings benefits. So next, I'm going to briefly describe how we implement this optimizer in Spark and then share some results. So we implement RESIN as an extension to the Catalyst optimizer in Spark. We add logical and physical operators for RESIN map and RESIN reuse. We introduce a new batch of optimization rules. One of these rules is the fusion rule, which does a single pass over the tree and does all fusion possible in this one pass. Next, we perform union and join elimination, where we check if after fusion, the multiple consumers of the fused subqueries, in fact, are going to both be joined or union, in which case, under certain conditions, we can eliminate this altogether. Finally, if this is not the case, we introduce an exchange and ensure that there are two parents which consume the result of this exchange. So we evaluated RESIN on TPCDS at 2 scale factors, 1 terabyte and 10 terabyte, and we used 2 different clusters to evaluate at these 2 scale factors. We performed a detailed evaluation of the 40 queries, which have more stages than necessary. And we'd like to point out that the baseline we are comparing against already does some basic IO optimization. For example, it pushes predicates and projects down to the store. Note that as data is in Parquet format, you can start eliminating columns and rows from the store itself. And the baseline also looks for scenarios where the data that's being exchanged at 2 different exchange points is exactly the same, in which case it can drop one of the exact exchanges. So I'm going to show a subset of results. More detailed results can be found in the paper. What this graph is showing is the speed up we see for queries, medium and high impact queries at a scale factor of 1 terabyte. We find that on average for these 25 queries, we can speed them up by about 1.4x, with some queries speeding up by as much as 6x. And we've seen the impact that RESIN has on disk before. What this graph is also showing is that RESIN is able to eliminate this IO without requiring additional memory for processing. Note that fusion increases the amount of data processed by each operator, but what this graph is showing is that the increase is not significant enough to have an increase in overall memory requirement of the system. So with that, I'll stop and I'm happy to take questions.